Thanks. So it's a great pleasure to be here. Thank you for the invitation to speak, and yeah, thanks to the organisers for a very interesting meeting. Yeah, I've very much enjoyed the last couple of days. So I'm Mark Wilkinson. I'm director of the DIRAC HPC facility in the UK, and so I've changed as well as changing the slot, I've changed the title of the talk slightly, and I've also emphasised that I'm talking about co-design. I'm focusing on HPC, but I'm also it's obviously in the light of the discussions we had yesterday, it's also very relevant for AI. The talk contains some science. I'll warn you in advance, and that's because at the UK HPC AI Advisory Council conference in last October, there was a comment made, which I think was quite fair, that a lot of us stand up and say, oh, it's all about the science, it's all about the use cases, and then we give a talk which is all about the hardware. And so in this talk, I'm going to try and do a mixture, so there'll be some science mixed in. In case you fall asleep, because it is the last afternoon, the conclusion is co-design of systems is worth the effort. So if you want to just remember one thing, that's the take-home message. So what is DIRAC? DIRAC is the HPC facility for the UK's theory community in cosmology, astrophysics, particle physics, and nuclear physics. And we have 4 sites, so Cambridge, Durham, Edinburgh, and Leicester. And we've got 4 different systems, and the architectures are tailored to different workflows. So I'll talk in more detail about how we arrived at these at the system designs in a moment. The project office is at UCL in London. And so we have a service starting up in the north in Edinburgh, which is an A100-based system, and that's focused on lattice QCD calculations, so theoretical particle physics. In Durham, we have the large-scale cosmological simulations being done on the memory-intensive system, where the large RAM footprint is a key component of it. In Leicester, we have the data-intensive service, and that is that's a heterogeneous system. It's a mix of AMD and Intel at the moment, but it's all CPU, and that's for various astrophysics and particle physics workloads. And in Cambridge, we have another heterogeneous system, the other half of the data-intensive service, which is a mix of it's Intel CPUs, but it also has NVIDIA GPUs. So I probably don't need this slide for this audience, but there's one point which is in bold, so that I don't forget to say it, that I really want to emphasize, and that is, so we're all aware that HPC is that simulation rather and modeling and increasingly AI are core research activities in most scientific fields these days. But what that actually means then is that HPC systems are scientific instruments. They're not just computers, as it were. And so what that, again, if you were going to build a telescope for astronomy, a lot of my examples, by the way, will be astronomy examples because I'm an astronomer by background. But if you're going to build a telescope, you would first decide what it was you wanted to look at, and then you would build an appropriate telescope. So that's one thing. That's why you should design the HPC cluster system that you're building around the use cases. Also, you wouldn't expect the government to tell you what kind of telescope to build, and you wouldn't expect the government to say, oh, you radio astronomers and you optical astronomers, you're both astronomers, you both need a telescope, so we're going to give you an X-ray telescope, and you can go and all do your science with that. So for those of you, if that reference didn't make any sense, essentially you can't combine different wavelengths of telescope at the same time. You can use them, but they do different things. They see the universe in different ways. So again, the right people need to be involved in the decision making, and that's a kind of nudge to those making decisions on who decides what systems we build, that it really has to be the right groups of people making the decisions. So obviously our models are getting increasingly complex, and that's because we're adding resolution. We may be adding new processes into the models. Obviously there's new types of models now with things like large language models. Increasingly we're coupling models on different scales, so you'll have a large scale simulation and then higher and higher fidelity simulations built into that. And one area which we briefly touched on yesterday is uncertainty quantification. That's kind of almost a dirty secret in many HPC communities, where you just kind of run a simulation. Maybe you run it twice, or you run it with a different code. If the answers look kind of the same, that's the uncertainty quantification. But actually, that's not good enough if we really want to understand and make sure that we're doing the calculations correctly. We talked a lot yesterday about the way that AI and HPC are now, and simulations are now all converging, and there's much more interaction. We're often building AI into the simulations, either to solve the equations or as surrogate models as part of the simulation process. Really importantly is it's not just hardware. People are really important, and software as well. And we've already just briefly talked about the need for more people coming into the HPC area with technical skills. And it's a huge problem in terms of software engineers, DevOps, ResOps, and all the other opses. We don't have enough people. It's very hard to find the people with the right skills. And so that's an area where I think it's great that the student cluster competitions are helping with that. So the approach we've taken in DIRAC is, given that we're trying to build a scientific instrument, we take use the scientific method for designing the system. So we start from a science case where we ask the community, what do you want to do over the next 5 years? Don't tell us how you want to do it in terms of what kind of computer you think you need. Just tell us what science you want to do. What's the scale of it? How does it compare to what you've done already? That gets peer reviewed, and then we are confident that we have an underlying business case for building a new system. We then go through a process of assessing the workflows that are needed, that have to be supported if we're going to deliver that science case, and that gives us our technical case. Again, that's peer review. That's the high level. What kind of services are we likely to need, and how big relatively should they be? And that high level definition then is also peer reviewed. And then we work very closely with industry partners over an extended period often to come up with technical designs. And that defines the actual details of what the services will look like and what will get deployed on the ground. So the outcome of that, as I said, is we have 4 different clusters within the DIRAC portfolio at the moment. And it means that we're able to deliver science which is actually much bigger in scope than you would expect from the size of the systems just on paper. So a nice example of this is the Flamingo simulation, which is shown here. So this is a simulation of galaxy formation in the universe. You're looking at a big simulation. The image on the left is a chunk of the universe. It's 1,000 megaparsecs on a side. And this simulation includes dark matter and gas. And what you see there is that over time, the dark matter collapses to form galaxy halos. The gas gathers in those halos, turns into stars, and then you end up with a universe that looks like the one we have around us. And the zoom-in bits show that as you look in closer and closer, in fact, in the 5 megaparsec box on the bottom right, sorry, I do have a pointer here. So in that 5 megaparsec box, this would be a galaxy, perhaps something like the Milky Way, which is our galaxy, and a neighboring large galaxy like Andromeda. So the idea is to try and reproduce the properties of the observed universe. And so this simulation was done by the Virgo Consortium. It's called Flamingo. It's the first of the Flamingo set of simulations that they're currently working on. It's the largest cosmological simulation, including gas, that's ever been done. They need more than just one. This is a digital twin of the universe, but you actually need multiple ones to assess what the parameters of the model should be. So they have to run it many times in order to compare how the properties of the galaxies change as you change the underlying model assumptions. So that makes it very expensive. But the memory-intensive service at Durham was designed specifically to do these kind of cosmology simulations, and so it's competing directly with systems which are 4 or 5 times as large in terms of flops and numbers of cores, but because of the design, people are choosing to do the runs on the Durham system rather than on the other ones. And that's a combination of factors. It's a large memory footprint, it's a non-blocking network, there's a large volume of flash for checkpointing so that you can very quickly checkpoint as the simulations go along. We also have a flexible model for the flexible approach to queuing, which means that you can get the large calculations scheduled more easily. So that's an example of where a system which is small compared to its international counterparts, by being able to focus on a particular set of workflows, is able to be extremely productive. Another really cool calculation that was done on the Durham system was looking at the formation of the moon. So the recent model suggests that the moon was formed by something colliding with the Earth. So something about the size of Mars called Theia collided with the early proto-Earth. And what the group at Durham, led by Jacob Kageris, showed was actually, if you go to what was originally thought was, when this collision happened, the debris would spread out. It would be essentially, you'd get a disk of debris, and then that disk would over time coalesce. Some of it would coalesce and you'd form the moon out of the debris. What they found is when you go to higher resolution, it's more complicated. And what actually happens is the debris breaks into 2 classes. One is an object which very rapidly forms the moon, and that's this blob here. And there's this other part which forms a debris disk and essentially disappears. And so the process, when you do it this way, when you do the simulation at high enough resolution, what they found is you form the moon very rapidly, already on roughly the orbit that it has now. And that has interesting consequences. By forming it rapidly, the crust is actually thinner than in more other previous calculations, which seems to match what you see in measurements of the lunar crust at the moment. It also means that they can look, because of the resolution, they can look at where the debris came from. So the debris is a mix of stuff from the proto-Earth and from Theia, the object that collided with the proto-Earth. And what they find is actually there's the outer layers are dominated by or at least have as much proto-Earth material as Theia material. So again, that will have an impact on what you'll measure when you look at isotopes on the lunar surface. So again, this is a simulation now where you're getting to a resolution where you can actually compare very directly with what's being measured. So now switching to, that was the Durham system, switching to our GPU-based system called TERSA at Edinburgh. So this was focused on lattice QCD, and I'll explain what lattice QCD is later. I just want to show, first of all, what the co-design process, what the benefit of the co-design process was in a kind of quantitative way in this case. So the system has 4 GPUs per node. It also has 4 NICs per node, and so it has extra communication, and again that was chosen because of the communication demands of the particular workflow. So the table here, I should explain, it's called TERSA. The reason it's called TERSA is that in Scotch Gaelic, TERSA is the word for megalith, so large stone, so hence the diagram of the stone circle. This is what it really looks like. So in terms of performance, what was measured by, so Atos won the tender. They were measuring 5.3 teraflops per node in terms of performance, but they actually committed to 5.83 when they in the tender process, and the network was above 160. And when I'm talking about performance here, it's not the theoretical flops, this is actual science flops that one of the lattice QCD codes was getting, called grid. And the interesting thing is that, so we went from, this was the comparison with our original system for a 16-node job. The measurement and commitment are shown there, so 1.28 was what they had 1.22 is what they had committed to, By the time of acceptance, they'd already exceeded that and got to 1.28. Then there was a period of technical commissioning. By the end, once we had gone through technical commissioning, which involved a lot of work with both between Atos, the EPCC technical teams, that's the Edinburgh Parallel Computing Centre team, and the developer, the software development team working on the grid code, the combination of that meant it was essentially a factor of 2 better in terms of performance for that workload. So again, that's where there was a lot of people effort went into it on all sides, but I mean the co-design essentially gave us a system which was twice as performant as the system that we had paid for in the tender. So now we're going to switch to look at what you can do in terms of particle physics with the system at Edinburgh. I'll just preface this by saying, as I said, I'm an astronomer, so this is, if you are a particle physicist, I apologize for anything I say which isn't correct. Feel free to put your hand up and object. So one of the key things that is of interest in particle physics is trying to understand the strong force. The strong force is it's important because you can use it to test what's called the standard model of particle physics, which is the theory that looks at all the types of particles that make up matter. And the strong force binds quarks into hadrons like protons and neutrons that we see in experiments, and probing them is what accelerators like the Large Hadron Collider, what they do. They try to understand what's going on inside hadrons, for example. And in order to connect the properties of hadrons that we see with the quarks inside them that we don't see, you have to have a theory, and that is called quantum chromodynamics. It's usually, in terms of numerical calculation, it's usually discretized onto a 4-dimensional lattice, and so it's called lattice QCD. So I'll just have 2 recent results to show from people who've been working on the Edinburgh system. So one of the things you can do, so there's 2 approaches to making progress in particle physics at the moment. You can bash things together harder, and essentially with higher and higher energies, and see what comes out. You can also look for very small discrepancies between theoretical calculations that you fully understand and what's seen in experiment, and see if any discrepancies that are significant actually point to things in the model that need to be changed. So one useful quantity for this is the ratio of the decay rates of 2 types of particles called pions and kaons. And in order to reach the kind of precision, because you can only obviously distinguish between different models if the error bars on the theoretical calculation are of similar size to the error bars on the experiments, and the experiments have incredibly precise error bars, so, incredibly small error bars. So I'm always impressed by the error bars in particle physics because I'm an astronomer. So in astronomy, an order of magnitude is pretty good, whereas in particle physics, you're talking about kind of, very, very small error bars. So in order to do that, you have to include more effects if you want to get the errors down. And one of them, one example of that, is in this decay that's shown here. So here you've got a pion, which is decaying into a muon and a muon neutrino. And normally, if you just did it with QCD, so quantum chromodynamics, everything you see here that's all you need to include. Essentially, you'd have the strong force deciding what happens in terms of the muon and the muon neutrino. But in fact, there's also interactions between the charges on the pion and the muon, and they're mediated by photons. So you've got photons exchanged in that. So then you need the other theory, quantum electrodynamics, has to be included in order to make sure you get the details correct. And so all of that was included in the point here on the right, which, as you can see, has relatively small error bars. This is the ratio of the decay rates for the kaon on the pion, and the pion is the one that's shown on the left. Now the problem is, you also have to worry about the fact the experimental measurement was done in the universe, which is effectively infinite on the scale of this kind of interaction, because these are subatomic particles interacting. So you have to extrapolate from a finite volume calculation to an infinite volume calculation. So this part has been done, so that's the value that was calculated last year on the DIRAC system. The errors here are based on the fact that we don't yet know how you extrapolate from the current volume, the current finite volume, to the infinite volume. That's the next set of calculations. But it's just to show, so this has all been made possible, and the small size of the error bars has been made possible by the A100 system in Edinburgh. Another thing you can do for testing new particle physics models is you may suggest that there are that there may be other forces that have to be included. And so one example of that is to understand why the Higgs boson, which is what the Large Hadron Collider discovered, the Higgs boson a few years ago, and it's essentially that's why particles have mass. However, the Higgs boson has a particular mass, and you want to understand why does it have that value and not a value that's slightly bigger or slightly smaller or even much bigger or much smaller. So that's called the naturalness problem. It has the value it has, but why? So one suggestion is that there's another force as well as the strong force, and that the Higgs boson is in a bound state in that force, and that then makes it kind of obvious that you would then have to have the Higgs boson with the mass that you see. And again, it's looking at mass ratios in this case, this particular model. You can, by measuring how if you're calculating the mass from using QCD, if you're calculating the mass of some fundamental particles, you can then see how the masses of the particles that you see, how they depend on the underlying masses of the quarks that make them up. And again, in order to do this correctly, you have to include lots of other factors, not just QCD. You have to include quantum electrodynamics. That's what you see on the left. So to show the complexity of it, that's the topological charge distribution that has to be included for one of the states that they're calculating. And this image I've included because it was the winner of the DIRAC research image competition last year for particle and nuclear physics. And the short version is the model that they're looking at is called an SU2 gauge theory with one adjoint Dirac fermion, and the calculations that they've done suggest it's conformal, and that essentially means if it is conformal, then it will have the properties that are needed to explain why the Higgs boson has the mass that it does have. And again, this was all made feasible by the fact that we had access to A100s in Edinburgh. So one of the things we've looked at with the system at Edinburgh is whether we can do anything about energy efficiency. We've heard a lot about energy efficiency over the last couple of days. It's obviously very important now that we use our resources as efficiently as possible. So Antonin Portelli, who's a professor at the University of Edinburgh, did a study based on the grid code, which is the code that was used that is used a lot in the UK for doing these particle physics calculations. And he did a series of tests, which I'll show some results from now. It was the benchmarks were based using the grid code, and there were two different sizes used. If you want the details, the report itself is at that link, and all the data and the environment and everything. So if you wanted to reproduce the tests yourselves, they're all online as well. So here you've got a plot showing the average performance, so that's teraflops per node as a function of the GPU clock cycle, so the clock frequency. So 1400 is the default on the A100s, and the two different calculations are shown here. This pair of lines, so green and red, are for the larger calculation, and then there was a smaller calculation shown shown below that. And so what you see is that at the peak, so at the default setting for the frequency, you have a performance of about 10 teraflops per node, and then as you decrease the frequency, the performance decreases. Likewise, on the right-hand side, you've got the power draw versus frequency, and obviously when it's at its peak frequency, it's at its peak power draw. Now, Antonin looked at how that power draw breaks down. So the total power draw from the previous plot is there. In red, you've got the GPU part, and in green, you've got everything else. So this was just a sanity check, basically. And so what you see is the non-GPU part is roughly constant, and it's essentially compatible. It's consistent with just being the idle power draw for all the other components. So it's the GPU part that really is varying with frequency, as you would expect. So the interesting plot is these two plots, and then there's a summary plot coming, but this is energy efficiency as a function of the clock limit. And what you see is the default setting is not optimal for this particular workflow in terms of energy. And so something around 1,000 megahertz or 1 gigahertz would be more optimal. Just note here, this is gigaflop per joule, which is something Antonin always makes a point of. Because he's a physicist, normally you'd see that as gigaflops per watt, but this is gigaflop per joule because the per second both cancel out. So this is a good unit to use. On the right-hand side, you've got how that affects performance. You've got performance as performance along the bottom and the relative energy cost. And again, what you see is you can have a reduction, a modest reduction in performance can give you quite a big saving in the energy. And this is summarized in this plot. So here you've said, along the bottom you've got epsilon, which is how much of an impact on performance. Obviously when you reduce the frequency, you're affecting the performance. How much of a hit on your science performance are you willing to tolerate? And what this shows is, and that's as a function of the frequency, and if you're willing to tolerate up to 10% reduction in performance, then you can actually clock down to about 1 gigahertz instead of running it at the default of 1.4 gigahertz. So the result of that is when you run the numbers through, you get something between 16 and 24% energy reduction. Very important to note, this is for this workload. We can get away with it on this system because it's dominated by this workload. So obviously it's more complicated when you have mixed workloads. Yeah, I've emphasized both of those already. The next step is to we've implemented this, so we have clocked the whole system down to 1 gigahertz, essentially as an experiment to see. We know that the usage is dominated by by the grid code. We're waiting for people to complain. So it's been 3 months now, and none of the other workflows have contacted us to say that they're very unhappy. So we're taking silence as happiness. We're also looking at whether we should allow users to control the frequency limits. That's something that's still under discussion, because it's certainly technically feasible to allow that. We also need to do larger scale tests with more accurate modeling, monitoring rather of the power. And we also want to look at the more complicated process of what do you do when there's multiple codes being used? What's the best way to do this? Because there are certainly arguments that say you're better off running flat out, get as much work through as you can, rather than trying to do this kind of tuning. And it certainly, that may be the case when you're looking at mixed workloads. The other thing we need to do is look at how this applies to CPU systems as well as GPUs. Okay, so now I want to talk a bit about our innovation program, and then I'll end with a new result about black holes, so a final bit of science. So along with the co-design program, we also have a lot of work with industry partners in order to enhance the science output of the facility. And so what we try to do is always have projects that are of real interest to both sides. So it's not just because it's not just that we're doing it for the sake of it. It's actually cases where, so we've done work with Gilad and his colleagues in NVIDIA networking, or Mellanox as was, looking at things which we have cosmology PhD students doing things on network things like DPUs. You might not think this is a connection, but actually there is, because they're trying to solve the same problem. It's just for different reasons. So the partners that we've worked with so far are shown there. There's also work we're doing now with the Save the Children charity and with Epistemic AI, so an AI company. And what we try to do is we've got a range. These vary from, we've done silicon level work with IBM and Intel, and then it goes all the way up to system development and then applications. So applying skills that our students and postdocs have picked up during their research and applying them in other fields. So one of the examples I just wanted to mention, basically because Gilad said I would in a comment yesterday, so I thought I'd better have a slide about this. So this is about a cluster that we have in Durham. It's funded jointly by DIRAC and ExCALIBUR. So ExCALIBUR is the UK's exascale program. It's mostly a software program, but it has some funding for testbed systems. So this is a Bluefield 2 cluster. It's 24 nodes, and it's managed by Alistair Basden, who's the DIRAC technical manager and who runs the other DIRAC systems in Durham. This is Bluefield 2 cards. It's an all-to-all HDR 200 fabric, and it's AMD cores that are in the nodes, and it's being used by a mix of ExCALIBUR projects. So there are software development projects for exascale, and Swift, which is the code that was used to do the cosmology simulation I showed you earlier, and to do the moon formation simulation. Now, the feedback in general is that there's work to be done. So these are a few examples of cases where there's actually been very solid progress on the system, but overall the HPC software stack still needs some work, and so that's something that Alistair's working with Gilad and others on. But there's some good things that have come out of it already. So where you have an MPI progression problem, so you've got threads that are stuck waiting, you can actually offload the work to the Bluefield card and allow those threads to continue work immediately without having to wait, and the Bluefield card can take over. A nice one is for task migration. So the Swift code, the cosmology code, uses task-based parallelism, and so an important aspect of that is being able to redistribute the tasks when you need to, and particularly if you have some nodes that are oversubscribed and some nodes that aren't, you need something to redistribute the tasks that used to be done just on the CPU, but the DPU can actually be used to do that intelligently and move the result back, so that the current, the task manager that's within the code doesn't need to know about it. So that's a very nice example of where the DPU can improve the code without the code having to be changed. And finally, data migration. Bluefield can be used to move data between nodes, again, without the CPU being involved. And it can also do things like sorting and reducing while it's doing that. So there's other benefits to Bluefield. There was a lot of talk about that yesterday. Okay. Right. I'm going to skip a few slides if you all close your eyes. So I'm going to show this one, and then I'll skip to the last part. One of the things that we've been doing with our placement program, which is another aspect of the innovation program, is we've done a series of placements on AI in the NHS, so in collaboration with Guy's and St Thomas Trust in London. And so this is an interesting paper. It's led by Hardy, who was a postdoc in astronomy, or is a postdoc in astronomy. The paper was published in the British Medical Journal, which is not the normal publication for astronomers, and it was looking at inconsistencies in one of the key diagnostic databases in the UK. So essentially, the various colors here are for 3 different conditions: a form of diabetes, a form of dementia, and autism. And what's significant about them is they're all things which, if you go to hospital and you have any of them, it's meant to go on your record every time. It's meant to be re-recorded and coded into every medical record that you have so that it can be tracked. And what the graph is showing, this is the percentage of so someone goes into hospital, and within 3 years they go into hospital again. This is the percentage of times that the second time they go in, it doesn't actually get recorded. So what you see is with diabetes, only 10% of the time is it not recorded. But for autism, it's almost 50%. It's kind of 45%. So that's really serious, because it means that this database, it's actually a requirement on NHS trusts that they record this kind of data. So the fact that it's being either not recorded or misrecorded is very serious, because it affects the validity of things you might do, because this is the database that's used then for diagnostics. So it's a very interesting result. This was done using machine learning, and I always highlight it because it's kind of an example of where there's huge benefit to working with people outside your normal community. Now, the last thing I want to say, I'll do very quickly. Just out of interest, hands up how many people know what gravitational lensing is? Okay. So I'll give a very quick tutorial. That's about half. So essentially, with gravitational lensing, you're looking at something far away, called the source. There's something in the way, which is the lens, and the light from the source is bent by the gravitational field of the lens. And what that means is, instead of you seeing the source where it actually is, you see other images of it. And what's been done using a combination of observational data and calculations done on the DIRAC system again in Durham is that they looked at this system where in the center, what you see there, that's the lens, that's an elliptical galaxy. In the background, you have another galaxy. It doesn't really look like this, but it's a star-forming galaxy, and so it's been stretched out. And the details of what this image looked like and this counter image are actually able to tell you a lot about what the mass distribution of this lensing galaxy is. Most importantly, it enabled them to detect a black hole that hadn't been found in that galaxy before. Because one of the things, black holes are important for the formation and evolution of galaxies, but the trouble with black holes is they're black, you can't see them. And so you can only see them if there's something near them that's going very quickly, so that's how we know there's a black hole in the Milky Way, or if there's gas around, and then you might see it because the gas gets hot. And so that's the typical ways that they're detected. But in a galaxy like this, you typically don't have much gas, and there's typically not any stars close enough to the black hole to do a detection from the motions of the stars. So this lensing technique actually allowed them to detect, I'll just show this one. So it's what you see here, that's the observational data. This is one of the images if there's no black hole in the lensing galaxy. And this is the image if there is a black hole. And so I'll flick them backwards and forwards. So it's hard to see in this, but if you go through the details, the one with a black hole at the center is a much better match to the observed data. The interesting thing is that number, it's 30 billion times the mass of the sun, so it's one of the most massive black holes ever discovered. Now, obviously, if you use a new technique and get a number which is very different to everything else, you always worry, is it right? So a lot of cross-checking's been done, and that mass, other ways of looking at of determining the mass are all consistent with this. So it looks like it's the discovery of one of the largest black holes ever. So in conclusion, all of the co-design work we do within DIRAC is designed to deliver the set of workflows that give you the science results that I've shown. So we would argue it really is worthwhile thinking carefully about what it is you want to do with the systems and then making sure that you tune them as much as you can to the workloads that you're trying to support. So that's the end of the talk. I would just like to say the next UK conference, we just confirmed the date of it about 2 hours ago. So it's the 18th and 19th of October in Leicester in the UK. And it's always sunny in Leicester in the UK, as you can see in the photograph. So I hope, especially in October, it's particularly sunny then. So I hope to see many of you there. Okay, thank you very much.